There are a number of things that we typically refer to, often even in just sort of a everyday life kind of situation, things we see in the news or talk about, that rely on logarithms to calculate. And when we talk about them, we may not know that, but in fact they do. We'll look at a couple of examples here, and you'll probably meet a couple more examples when you go to do your homework. Logarithms we often use because they're much more convenient if we're discussing and comparing either very, very large or very, very small numbers. This happens a lot in scientific applications. Here's our first example. Seismologists measure the amplitude, or in other words, the height, of seismic waves, which are disturbances in the ground. They do this, of course, because once disturbances get big enough in the ground, we can feel them, and we call them earth tremors, or if they're large enough, earthquakes. The amplitude of the smallest measurable seismic wave is called the reference amplitude, and I'm not going to give an actual value for it. Scientists just typically write it as A with a subscript of 0, or A naught. When an earthquake occurs, seismic waves are measured and described by stating how many times larger than the reference amplitude they are. So I might say the earthquake had amplitude or waves of an amplitude of 10 times A naught, or 1,000 times A naught, or 1,000,000 times A naught. The size of the earthquake, then, is described using what we call the Richter number, and that's found by taking the logarithm of the comparison of the size A divided by the reference size, A naught. All right, we're going to take a look and compare 3 earth tremors. Seismic waves on the first are 1,000 times as large as the reference amplitude. So 1,000 A naught. Second one would be 10,000 times the reference amplitude. And then the third one is 100,000 times the reference amplitude. We're looking for the Richter number for these earth tremors. So let's see. The first one, our amplitude was 1,000 times as big as the reference amplitude. That means to get the Richter number, I take the logarithm of the amplitude of this earth tremor, which is 1,000 A naught, divided by A naught, which is just the logarithm of 1,000 when you cancel the A naughts. And keeping in mind this is a common log, base 10, it's 10 cubed that gives us 1,000. So that logarithm is 3. In the next one, our seismic waves are 10,000 times the reference amplitude. So A is 10,000 A naught. And that means my Richter number, I take the logarithm of my amplitude, 10,000 A naught, divided by A naught. Once again, those A naughts are just going to divide out. So I have the log of 10,000. Which either you know that 10 to the 4th power is 10,000, or there's a little trick with powers of 10, right? You can just count the zeros, and that actually gives you the exponent. So 10 to the 4th power is 10,000. Finally, our last one was 100,000 times as big as the reference amplitude. 100,000 A naught. So when I set up my calculation for my Richter number, I end up taking the log of 100,000 A naught divided by A naught, or in other words, just the log of 100,000. And 100,000 is 10 to the 5th power. So base 10, I would need an exponent of 5. Again, notice the little shortcut of counting the zeros. What I want you to especially notice about this is that the Richter numbers really are hiding the difference in the size of these earthquakes or earth tremors. This one is 10 times as big as that one, right? 10,000 times the reference amplitude compared to only 1,000 times. And yet its Richter number only goes up by 1. This one is 100,000 times as big as that one, but its Richter number is only 2 more. So when you look at Richter numbers, unless you understand the logarithmic scale, the fact that those numbers are really exponents, you can really miss the fact that a small change in Richter number is actually a very large change in the amplitudes or disturbances of the ground that is causing the earthquake. Let's do a couple more earthquake examples. We'll use real earthquakes this time instead of ones I made up. In 2010, we had one of the largest earthquakes in recorded history in Chile. The seismic waves were 6.31 times 10 to the 8th times as big as the reference amplitude. The largest ever measured was also in Chile. Probably not a good place to hang out for earthquakes, I guess. Back in 1960, it had a reference amplitude of 3.16 times 10 to the 9th times the reference amplitude. We're going to find the Richter number for both earthquakes. So I'm going to start with the one that occurred in 2010. To get my Richter number, I take the logarithm of the seismic waves were 6.31 times 10 to the 8th times as big as the reference amplitude. I divide that by the reference amplitude, and as always in this calculation, those just cancel out. And now this is not something that I can do mentally. It doesn't come out evenly. So I'm going to go ahead and grab my calculator here. This is a common log, base 10, of 6.31. And there are a couple of ways that you can actually put that times 10 to the 8th in your calculator. You can write it right out, 6.31 times 10 to the 8th, giving us just about 8.8 in fact. Or, and science teachers often use this method, scientific notation is so common that they use a little shortcut which actually exists right on your calculator also. Above the comma, this double E actually just gives you an E when you type it. And that automatically means times 10 to whatever power you're going to put in. So then all I have to tell it is E8. And that's just kind of calculator shorthand for times 10 to the 8th. Notice, of course, I get the same thing because that was really the same number that I put into both of those. So that one's got a Richter number of 8.8. What about if we go back to the 1960 earthquake? To calculate the Richter number, I take the log of the amplitude, 3.16, times 10 to the 9th times the reference amplitude, A naught, over A naught. And then once again, I need my calculator to do the calculation here. I have the common log, base 10, of 3.16, and let's just practice that E for times 10 to the 9th. We've got just about 9.5 there. So a couple of the biggest ever earthquakes had Richter numbers of 8.8 and 9.5. All right. We'll look, as I said, at one more application right now, but there are a number of them, and you'll meet a couple more in your homework. In the next one, we're going to look at pH as our example. And we often talk about pH in gardening. You have to have the pH of your soil at a certain level to support your plants. If you have a swimming pool, the pH of a swimming pool is important to protect people's skin, as well as make sure that you've got the ability to keep it clean with the chlorine. So we know pH is used for various things. In chemistry, essentially the pH of a solution, that number tells how acidic or how basic the solution is. Pure water is neither an acid nor a base, and it has a pH of 7. Acids have smaller pHs, less than 7, and in fact the lower the pH, the stronger the acid. Bases have a pH greater than 7, and again the higher the pH, the more basic the solution is, the stronger the base. So the closer to 7, the closer to neutral. Further away from 7 you get, the stronger the acid or the base. To calculate the pH of a solution, chemists measure the concentration of hydrogen ions, which they use the abbreviation H+, in moles per liter, that are in their solution. pH is the opposite of the logarithm of that hydrogen ion concentration. Here are a few things to practice our equation with. Human blood in a healthy person has a hydrogen ion concentration of 4 times 10 to the negative 8th moles per liter. Let's find the normal pH of human blood and determine whether it's acidic or basic. So our equation says take minus the log of our hydrogen ion concentration, 4 times 10 to the negative 8th. So I have negative log 4, and the same deal. You can write out times 10 to the negative 8th, or you can use the little shortcut and just say the exponent on the 10 is going to be negative 8. And it looks like it's about 7.4. So, with a pH of slightly more than 7, just a little bit more than the neutral of water, human blood is slightly basic. All right. There's a disease that actually results when the hydrogen ion concentration gets too high. It's actually a severe condition called acidosis, which can even result in death. Suppose we have a blood sample from a patient with acidosis, and they have a hydrogen ion concentration of 1.2 times 10 to the negative 7th moles per liter. I'd like to know the blood pH for this patient. So I use that same calculation. pH is minus the log of that hydrogen ion concentration. And I get about 6.9. Now notice the pH isn't all that much different, although we did talk with earthquakes about how a small difference when you take a log can actually be a much larger difference in real life. But the big deal here is that while human blood should be, in the normal case, just a little bit on the basic side, notice that this blood sample is just slightly acidic. which undoubtedly is where the name acidosis came from for this particular disease. All right, one more. Hydrogen ion concentration in orange juice is 4 times 10 to the negative 4th moles per liter. What's the pH for orange juice? Is it an acid or a base? You probably already know the answer to that particular part of the question, but let's go ahead and do the calculation. We'd have minus the log of 4 times 10 to the negative 4th. About 3.4. And notice that's quite a bit further away from 7 than anything we've looked at so far as the blood samples. Definitely an acid. I'd like to do one more thing with this. I'd like to find the ratio of the hydrogen ion concentration in orange juice compared to the hydrogen ion concentration in blood. And then also take a look at how that relates to the difference in their pH values. Okay. So let's see, ratio. The concentration in orange juice is the one I just looked at. Let's just do OJ over blood. It was 4 times 10 to the negative 4th moles per liter. And back up in part A, normal blood sample had 4 times 10 to the negative 8th as its hydrogen ion concentration. We could certainly do this ratio or this division on the calculator, but it's actually not difficult to do, even just by hand, because notice the 4's here would divide out to 1. And if I subtract these exponents, negative 4 subtract negative 8, negative 4 plus 8 would be 4. So the ratio is actually 10 to the 4th, or 10,000. The pH of orange juice that we just saw here was 3.4. And the pH for blood that we saw back in the very first problem on this page was 7.4. And what I want you to particularly notice is the exponent is exactly the same as the difference between the pH values. We go back to that idea that the logarithm is really like a missing exponent, right? It's an exponential or order of magnitude designation. The fact that the difference here is 4 is actually a difference in 10 to the 4th times as much hydrogen ion concentration. So logarithmic scales are handy. They mean that we don't have to spend a lot of time dealing with things like 10 to the 8th or 10 to the negative 6th or things like that. But we do have to be aware that small differences in a scale that's designated as a logarithm are actually large differences in what they're measuring. All right, that brings us to the end of 2.7.